Shall I introduce him then?
Okay, so I started the recording now. So it's a pleasure today to have Aaron here, and we get an introduction by David at the moment. So I hand over to David, and David hands over to Aaron.
Okay, so Aaron King is professor at University of Michigan. He has worked a lot on several problems of inference from data in the context of disease, all kind of disease from childhood diseases to malaria, all kind of things, and he is very much interested into the general problem of getting information from data through dynamical models, and he's giving us. We are very lucky about it because he is giving us this talk on efficient scientific inference using stochastic dynamical systems.
Thanks, David.
And yours, Aaron.
Okay. Thank you very much. Yeah, and thanks to David and the rest of you for inviting me. You know, it's a very small window that I'm looking through to see you guys, and but I'm very excited to try to pass some ideas through that window in both directions. And so I hope you will feel comfortable asking questions at any point. I can't see you at all. I have just the very smallest. I mean, it's literally a very small window as well as metaphorically. But you know, by all means, interrupt and ask questions. Maybe David, you could monitor the chat, and or whoever would like to do that, and interrupt me if there are questions that come up that require some clarification. But anyway, so yeah, I'm very excited to talk about some ideas that I've been working on for a long time, and some methods that I think are of quite general value and quite interesting from a scientific point of view. Before I get started, I'll just make sure I have a chance to thank the many students, postdocs, collaborators that have worked with me on various aspects of this stuff. You know, the first line are postdocs, the second line collaborators, and there's been some funding as well. David, in fact, I met him through the working group there that's mentioned at the bottom. But so of course, you know, I think this group is quite familiar with the use of models, many of the uses of models, and it's quite commonplace to point out that, you know, models have many purposes, right? So at the very minimum, you know, often they help us to organize data, but of course we can explore various theoretical principles through and develop various theoretical principles through modeling, exploring hypothetical scenarios, and that of course has an important role in policy. But what I want to focus on today is using models in the scientific sense, in the scientific mode of explaining patterns that we observe in data. So when we're trying to understand biological phenomena, for example, the progression of infectious disease through populations or within hosts, we really should think about models as tools for looking at the data, in particular, like scientific instruments, like a microscope or a telescope, for looking at the data. And the reason that they serve this role, if you think about it, is because they focus attention on the discrepancies that exist between our hypotheses about how a system functions and reality as revealed in the data. Right? So they tell us which features of the data are to be expected on general principles and which features of the data are anomalous or surprising. And so from that point of view, a model serves a very, very specific purpose. Of course, as soon as you ask that question, what are the discrepancies between the model and the data, and which ones are big and which ones are small, it's a question of how you quantify those discrepancies. In order to do that, sort of the modern approach to doing that is an information theoretic approach that requires that we model the error so that we actually probabilistically describe the errors that we make. So what do I mean by that? Let me give you some examples. Let's see. Is this going to work? Yes. All right. So if we think about trying to understand biological systems, of course, the best way to understand many biological systems is to manipulate those systems, to perform scientific experiments in those systems. But a variety of different, many biological systems either can't be experimented on for various reasons of scale or of ethics, or are damaged when we experiment on them in some ways. So if we want to study intact biological systems, the key tool that we have is the dynamics of those systems, because it's through the dynamics that the causal mechanisms that shape the behavior of those systems are revealed. So, the flip side of that, the reverse of that observation is that when we have hypotheses about the causal mechanisms that structure a system, those can often be formalized in a fairly straightforward way as dynamical systems models, right? So we write down equations that describe the causal forces and how they connect to one another. And then the straightforward implication of those models are the unfolding dynamics through time. So, so that's the sort of background or the basis, the philosophical basis of what I want to talk about today. And of course, practically, the problems that we face are problems of inference. So in particular, of course, how do we estimate the unknown parameters? There are always unknown parameters in these models. When we have multiple competing hypotheses expressed as different models, how do we decide among them? And how can we more generally extract the most amount of information possible from time series data, from data, whatever data we have, but time series data are particularly revealing about dynamics. And an interesting question, of course, is at any given point, how do we know when we need a better model, right? When we need to improve our theory, and how do we know when we need to get better data? So those are some of the questions that I think are interesting to think about. So as I say, the key principle that focuses all of this and gives us some traction is the idea that we're going to probabilistically model the error. And so we should think about error where it comes from, of course. And if we're going to model it, we need to think about its sources. And of course, measurement error is the most obvious one, right? Our instruments are imprecise, sometimes quite inaccurate. And so measurements of biological systems are famously noisy. But in addition, of course, there are other sources of probabilistic or stochastic fluctuations, right? The biological systems exist in an environment which is never constant, despite our best efforts, when we can even make those efforts. So there are trends in environmental variables, ambient temperature, population size, vaccination coverage, and so on and so forth. And there are fluctuations in these things, some of which are predictable and some of which are much less predictable. There are inevitably heterogeneities in the population we are studying, right? If any group of biological organisms, any group of cells within an organism, there are heterogeneities there that we are forced to ignore, partly because we never know about them all, and partly because our desire is to understand, not merely to catalog all possible complexities. So there are heterogeneities, differences among individual units that every model must ignore. And one way is sort of the best way, perhaps, to, I would argue, to nevertheless account for these heterogeneities is through stochastic terms. Right? We represent the components of the model that are missing in the form of stochastic terms. Our models are also sometimes wrong, right? I mean, not just incomplete, but actually misspecified. And that can be a very difficult problem if one ideally would like to perform inference in such a way that such misspecification would become evident through time and with exposure to data. And of course, finally, there are many variables, and this is sort of implicit in what I've already been saying, there are many variables that are left out of every model. And one way to sort of account for those, to allow them to be there without their absence, to avoid their absence biasing things terribly, is to account for those things using stochastic effects. Okay, so here's what I want to talk to you about. I want to first present a class of Markov models that are very useful and very, very broad class of models. In fact, many, many interesting models fit into this category. I want to show you some examples in terms of two particular disease transmission systems that I've studied. And then I want to go a little bit more into the mathematics of it and talk about different kinds of formalizations and methods for dealing with these things. So the simple example that I think is canonical that I want to kind of all of us to have in the back of our minds is our compartmental models of stochastic transmission processes. So the classic example is the SIR model, the most basic Kermick-McKendrick SIR model, where the population of hosts that are susceptible to infection or capable of being infected is divided into three categories vis-a-vis their infection status. So individuals that are susceptible are in the first box. Can you guys see the mouse cursor?
Yeah, that's perfect.
Yeah. So in the susceptible box, the infected individuals are here and the recovered individuals are there. And the process of infection spreading through a population is modeled as the movement of individuals between these different compartments. So there may be births that lead to increase in the number of susceptibles because babies perhaps are susceptible to this infection. And of course, deaths can occur always, as well as infection progression. So all of the different processes are represented here in terms of different arrows connecting these boxes. If we focus just on the first two boxes and the processes that directly involve them, then we might end up with a system of equations that we derive as follows. So if we let X and Y be the occupancy, the number of individuals in each of those compartments, and the rates at which individuals move between the compartments being B for the birth rate, lambda for the infection process, and mu for the death rate. Here I'm just, for simplicity, assuming there's only infected individuals die. Then we can write down a system of equations in a bunch of different ways. And I'm much less interested in exactly how we write down these equations. Here's one way of doing it, as I am in the sort of overarching mathematical properties of these things. So this is just a stochastic differential equations approach to writing these equations down. And I think there was a slide that got skipped. So let's look here. So the easiest way to do that is to think about the number of individuals that move from X to Y in any interval of time, call that n sub xy, and the number of individuals that leave Y because they die, we'll call it ny null. And then to model the increments of those processes in terms of a stochastic differential equation, mean term and a stochastic variability term. This is just an example of how one might do that within the context of the so-called Ito diffusions. But of course, as I say, there are many different ways of doing it. The key thing is that this is a stochastic process, right? So it's a process that's stochastic, that accounts for variability for all the reasons that I was describing before. Because stochasticity is really there.
Yeah, maybe I mean, it would be maybe good to ask a question about that, because
absolutely.
I mean, you're right. I mean, I absolutely agree with what you say, but of course, this is a very special kind of noise, completely uncorrelated and so on. So, you put implicitly again a kind of hypothesis into your approach with that.
Well, yeah, I mean, and I don't want to focus too much on the specific form of equations because the methods I'm going to describe apply to a much broader class of models. But you raised some interesting points, right? And I mean, let me just go to the next slide and then I'll address those things. So if we actually then think about the changes in the occupancies, we end up with a particular structure, both in the mean, but also an interesting correlation structure. So the uncorrelated assumption of the previous slide becomes a particular correlation assumption here. But regardless of that, you raised a really interesting point, which is that some of the hypotheses that we want to talk about are hypotheses that are really at the heart of our scientific questions, and others are sort of added for mathematical convenience, right? And it's important to be able to distinguish between those two when the data start to push back and tell us exactly how we're wrong, to be able to identify whether the reason for our error is an interesting reason or a sort of an uninteresting reason. Or, well, interesting to the scientist or interesting to the mathematician, perhaps is a better way of saying it.
May I have a question?
Yeah.
Yeah. So the so going back to the noise, to your choice, wouldn't it be more natural to look at this problem considering a Poisson process?
Absolutely, absolutely. And in fact, that's what I would typically do, right? But I wanted to throw this out there. You know, there are lots of different ways to write these things. More natural for some purposes, perhaps much more natural. For other purposes, inconvenient, perhaps for other reasons. But there are, for example, all of what I'm going to describe to you today would apply if we were talking about a general continuous time Markov process with discrete states or continuous state. In fact, it's quite general. So you'll see when I get to that, this is just meant to be an example so we have something concrete in our mind when we're talking about these kind of stochastic processes, because you know there are lots of details, but really I'm going to talk about things at a much more general level. Okay, so let's look at some examples again to make it a little bit more concrete. So cholera is a terrible infection that's caused by a bacterium that typically is passed through the fecal-oral route and causes, you know, acute disease and mortality, at least classically speaking. And it appears to have originated in the region just lying to the north of the Bay of Bengal. And so a study I did a number of years ago involved looking at this region of endemicity and looking back into the historical period when both the disease was raging unchecked because people didn't really understand what it was or how to control it, and also where records were kept. So in particular, the British administration of that region of the world at that time kept very good records on the extraordinarily large numbers of people that were dying as a result of cholera. And these are some examples of what the data look like. So these are 50 years of monthly cholera death records from the districts that I showed you in the map, 3 of the districts I showed you in the map. And then we see really interesting dynamics, right? There's a sort of, in Dhaka, one of the larger, more urbanized areas, you sort of see an epidemic every year, some years very severe and some years much less so, with the hint of some overlying multi-annual cyclicity to it. Interestingly, there's a strong seasonality, which is quite peculiar to cholera. There's actually 2 peaks per year of cholera in that region of the world during that period of time, and to some extent still today. And then as we move down the coast, down towards the coast, we see, up away from the coast into the north, we see dynamics that are marked by a much more explosive pattern with long periods of very low incidence. And if we move in the other direction, down towards the seacoast, you see patterns where quite the opposite seems to happen, where the troughs of very low numbers never get quite as low. And in some years, there are cholera deaths all year round. So a very interesting, very rich dynamical pattern with many different replicated or across space as well as through time. And one can ask, you know, sort of what can we learn about cholera from studying these things? So the kinds of questions that are interesting here, and these remain interesting today and really quite contentious, are the relative importance of human-to-human transmission. So transmission, say, within a village or within a household from one infected person to another versus environmental transmission. So I didn't mention it, but the bacterium can live on its own outside of the human host in the environment, in the brackish waters, which are quite common in this part of the world. And so there's a lot of attention has been focused on that route of transmission from the environment into the human. Important questions surround how long immunity to infection lasts. It's been very difficult to devise effective vaccination strategies against cholera. Certainly not as effective as we'd like them to be. And why is that? The role of the environment, the seasonality of the environment, and possibly a longer timescale environmental drivers are important. And then the importance of the ecology of the bacterium in its free-living state, in particular, its interaction with various viruses that attack it. So one way to go about addressing these questions is to translate them into models. And so building off of the ideas that we had before, perhaps we start with something as simple as this. but we have to deal with the fact that cholera immunity doesn't appear to last for the rest of your life. So there is a passage from recovered back into the susceptible pool. People can become infected more than once in their life. Of course, in addition to the human-to-human transmission that was already present in the model I showed you before, there's transmission from an environmental reservoir. There's seasonal modulation for reasons that are not very well understood in potentially both of those pathways. So different seasons may have more or less transmission. There are deaths that occur, it's quite a large number of deaths that occur because it's a highly fatal disease in this period of time. And then of course there are other feedbacks as well. So infectious individuals shed bacteria into the environment. The environment involves the interaction between the bacteria and vibriophage, so viruses that attack and kill the bacteria. And so that can potentially modulate things as well. So there's a hierarchy here of complicated models nested inside of one another in some sense that encapsulate many of these hypotheses. And one would like to be able to say, well, what do the data that I showed you have to say about all of this, right? There may be multiple mechanisms here that are capable of explaining the patterns in the data. Is there nevertheless information in there to discriminate amongst them? So these models, it goes without saying, are of course nonlinear, they're stochastic, they're non-stationary, they're driven by pronounced changes in population size during the period in question, as well as environmental fluctuations and other extrinsic drivers. So they have a bunch of complexities that make them quite distinct from the toy mathematical models that we see in the textbooks. So the questions we want to ask is, how well do each of these models, the whole model or any sub-model that's embedded in it, how well do these explain the data? And more importantly, what insights can we gain into how the system dynamically self-regulates over this time period using these models? So the important thing that I want to point out is that the process of deriving these models is one that is entirely focused on the scientific questions and not on the issues of mathematical tractability, or not to a very large extent on the issues of mathematical tractability. Obviously, we've written down some equations. They've got 8 or 9 variables or something like that. That's a lot less than the number of variables that are in the system in reality. But the point is, we're not restricting ourselves to some class of models that we know how to work with, because we want to be able to let the science dictate the models that we look at. Okay, so to return to the scientific questions, I mean, this is just a restatement of the scientific questions. All right, another example. I'm going to come back to the cholera example in a little while, but another example that I've worked on is to do with the ongoing resurgence of pertussis. So this is another bacterial infection. It's a very different bacterial infection in just about every way, but it causes quite acute disease in young children and is responsible for an appreciable amount of mortality around the world. Interestingly, there are effective vaccines for pertussis, but even in places where the vaccine coverage is high, we see a resurgence of the disease in recent years. And this is what this kind of looks like. In Massachusetts, these are annual cases of pertussis in that state in the United States over the large part of the 20th and early 21st centuries. And you can see that the introduction of the vaccine in the late 1940s resulted in a massive decline in overall incidence. This is a log scale here. Question? Is there a question? No? But then beginning in the late 1970s, you see this sort of a rebound. And still, this is log scale. So, this whole period in here was almost unnoticeable, right? Very, very small numbers of cases through here. And it's only quite recently that we begin to become worried about this. That's coupled at the same time with a pronounced shift in the age profile of infection. So in the early days of pertussis, these are some data showing the distribution amongst ages. So newborn infants are here on the left, and then older age categories are over here on the right. And you can see that it was largely a disease of young children, in fact, preschool to early school age children. Whereas in the more recent period of time, this is up here in the early part of the 21st century, you can see that there's really a pronounced peak in the teenage years. So it's a real shift in the age profile of infection. In addition, if you look across countries in the world, in all of these countries, vaccination is widespread. You see a mixed pattern of pertussis resurgence. So here, the lines in black show the base 10 logarithm of incidence in each of those countries based on WHO data. And then we've sort of done a very simple statistical analysis to sort of characterize them as to whether they're declining. For example, in Spain, they were declining for a long period of time, and then recently they've been increasing. This data is only up to about 2011, so it's a bit out of date. So I don't know what's going on there right now, but it's a bit of a resurgence there. So similar to the picture in the United States, which is somewhere here. Here it is. Well, actually, in the United States, the picture was across this entire period from the 80s through the period. It was just increasing steadily through there. The background colors represent the coverage, the vaccine coverage. So the denser colors are higher coverage. And there's a vertical dash line which indicates when countries switched from a killed whole cell vaccine to a synthetic acellular vaccine. And so many of the hypotheses surrounding the resurgence are to do with the shift in the vaccine coverage. And you can see in Spain, that sort of looks very attractive as a hypothesis. We see that it's declining and then the vaccine changes and now it's increasing. In Portugal, unfortunately, it's not quite so simple, right? It was declining and then it started to increase before the vaccine was really changed. In the United States, it was increasing the whole time. Sorry, question? I think we have a Zoom moment going on here.
Oh, yeah.
In People's Republic of China, it's declining throughout. So it's really a heterogeneous picture. And we were interested in trying to see what we could see. So many of the basic hypotheses, the hypotheses that have been put forward to explain the resurgence really don't do a very good job of capturing the full range of possibilities. So here's a list of possible hypotheses that have been put forward. As I say, changes in vaccine efficacy, possibly the evolution of the pathogen, increased circulation of other pathogens that may behave very similarly, asymptomatic transmission, and so on and so forth. In all of these hypotheses, the key unknowns have again to do with the durability of the immunity that's induced by the vaccine and the relative efficacy of vaccine immunity to infection-derived immunity. So how efficacious are these things?
Just one question about that.
Yeah.
Is the policy of vaccination more or less the same in every country?
No, it's highly variable. Oh. It's quite variable across countries. Yeah, which is a very interesting class of problems in itself, right? Absolutely.
Yeah, so it's not only the durability, it might also have to do with the policy of when.
Absolutely. I mean, these are some key unknowns. These are not the only unknowns, right? Okay. These are some common threads that run throughout, but they're by no means is this the end of the story. So again, one can attempt to translate some of these hypotheses into models, right? And so here things are a bit more complex because individuals can be born, individuals can be vaccinated, and vaccinated individuals are presumably at a lot lower risk of being infected. But of course, the vaccines can fail. And so in this study, we were interested in trying to understand if we could see how vaccines fail. And there are actually three different ways the vaccines can fail. There can be a sort of a primary failure where the child is immunized, but the immunity never really arises. The antibodies never really come up for various reasons. The vaccine, of course, can lose its efficacy through time, right? We can have a waning of immunity that leads vaccinated individuals to become susceptible again. And there can also be what's called leakiness. You can be vaccinated and still infected. You have just a lower chance, perhaps, of being infected than if you were unvaccinated. So that's called leakiness. So these individuals can become infected in this way. And so when you can translate some of those hypotheses into models that look like this, where you have these different routes of these different progressions of infection in unvaccinated and vaccinated individuals. Immunity is believed to be long-lived if you do become infected. So there's no arrows leading out of the R box. The data come in the form of case reports. So individuals that are diagnosed with pertussis, and we model those as being measurements of the flows off between the eyes and the R compartment. The force of infection, which is the rate at which susceptible individuals become infected, is a little bit more complicated in this situation. So there is the usual sort of dependence on the infected individuals here, but of course, individuals who were previously vaccinated and infected can also transmit, but perhaps at a different rate. So theta here modulates that rate. And in addition, individuals that are vaccinated and infected may be more or less easy to observe, right? They may be more or less symptomatic, and therefore perhaps observed at a reduced rate, where eta represents the reduction in the probability of reporting an individual from this group versus from this. So the questions, again, that are running around in here have to do with the nature and durability of vaccine-induced protection. So how much primary vaccine failure is there? Is there waning? And if so, what's the time scale of that? Is there leakiness? And how can we describe that? More generally, which models explain the data well? And of course, to answer any of these things, we have problems in inference, in parameter estimation and model selection. So we use data from the US state of Massachusetts that looks like this, and I won't spend a lot of time. These are monthly reports of cases across about 15 years from Massachusetts, and broken down by age into different age categories. These show the sort of long-term trends in those age categories. So some pronounced increase amongst the older population, and something of a very slight decrease amongst the youngest infants. This is a frequency diagram that shows the different age categories. You can see that decrease in the infant frequency here, with somewhat of an increase in the teenagers and in the adults. And then, of course, from year to year, there's a lot of fluctuation as well. So in order to address this model, we need to complicate the model more, because we have data that's resolved to age. And so we want the model to represent that. And so this is just meant to indicate, what I've done here is sort of, now each of these layers represents a different age category. And in addition to disease progression through here, there's also the aging process. So individuals get older at a deterministic rate. So, so these models, again, are not convenient for doing mathematics on. They're high dimensional stochastic processes with a large number of parameters and lots of complexities, like time varying covariates. This is the vaccination rate, which varies through time, the population size and age distribution, which varies through time. Here, the birth rate is declining across this time period in a fairly substantial way. If you more than 10%, shifts in the age distribution and so on. In addition, there's a large number of parameters associated with the age-structured transmission process. How are these different age groups in contact with one another? So this is just a diagram meant to represent the sort of contact structure associated with life in an industrialized society. Yeah, question? Is there a question? No? So this is kind of a stylized artist depiction, but you can notice that we have a matrix here of different ages. It's a square matrix where we have ages in the rows and ages in the columns. And then there's a contour diagram here which describes the intensity or the rate of contacts between these different age groups. So along the diagonal here are contacts within an age cohort, so most notably in school. And then there are intergenerational contact rates here along these subdiagonals.
So maybe I actually have a question. So
yeah.
From the previous slide, so you have just overlaid all the models because you you introduce the age structure. So, but what you are saying now in this slide is, let's say, also the how these different overlaid models are linked to each other. So you have
exactly
cross rates between the structures.
Not birth rates, but contact rates.
Contact rates between the age. And is that, how did you parameterize that?
I'll show you. I'll show you.
Okay, yeah. Okay.
I mean, it's a very important question because it's quite clear that there are these strong differences, and yet to parameterize them is not easy. So there have been a number of studies that have aimed at trying to parameterize these just using direct observations. So most famously, the Polymod study, which was a diary-based study. These are the results of the Polymod data. This is based in Western Europe. And you can see, so here these are equal size age categories, so the diagonals are truly diagonal, but you can see the really high intensity associated with children in school, and then things drop off quite a bit. These are the intergenerational contacts here. There are other approaches that are based upon different data. It's quite an active area of research to try to really get at these things. We also applied data from a study based on Massachusetts census data, together with a fair amount of theorization. The papers are here. We can talk more about that if you're interested.
Yeah.
But basically, we want to use all of these things to parameterize this model. So we should talk about how to go about accomplishing this. Now that you've got a sense of what these models look like, so from a mathematical point of view, these have a particular structure, the structure of a partially observed Markov process. So we've got some kind of, in all cases, a Markov process here, and we're interested in the causal forces whereby the variables of this actually affect its own dynamics, but we don't observe that process. Oh, I should say that process, of course, is affected by external variables. And there's a process by which we measure the variables, and that's how it gives rise to the data. So if we want to actually extract information from the data, we need that information is going to flow in the reverse directional from these causal forces. Yeah, another question? No. So the mathematical setup is that we have some times at which observations are made and some data. We have some kind of unobserved Markov state process. So all of those state variables in the models I was showing you before, all the compartment numbers and so on. We have some kind of a measurement process. And the unobserved process, which is typically the thing we're most interested in as scientists, is represented mathematically by some kind of a transition probability density. This is a Markov process, so it just depends upon the state variable at this time and the state variable at that time. There's some kind of a measurement model process, which is represented by this probability density function, and then some initial state distribution. So this is the mathematical underpinnings. The central problem that we have is to try to estimate the parameters and compute likelihoods, right? And so the likelihood function is written here. So it's the joint density of the observed variables evaluated at the data. So the stars here represent the data. And if we write that out as an integral, right, we're going to integrate out this joint density here of the unobserved and the observed things across all of the unobserved variables. So because of the partially observed Markov process structure that has a form which is a bit simpler than this general form written here, right? We can factorize it into a sequence of different things, one for each observation interval. This is the initial density, the state transition density, the observation density, and of course, all of these things are conditionally independent on one another. That gives rise to this structure, which is really another way of saying that it's a partially observed Markov process. All right. So as I say, the process of computing the likelihood involves solving that integral, which is typically an extremely difficult thing. The traditional solution is to be quite clever, right? Meaning one wants to modify the model so as to make it as easy as possible, which is unfortunate, right? Because we may be forced to compromise some of the questions that we want to answer. And then often, even with a carefully chosen model, one has to sort of design the inference algorithms suited to that model. So for example, an MCMC sampler has to be tuned to give adequate inference on a particular model. And so the problem you run into when you're doing this is you're to some extent, using the data to answer the questions you have, but you're never quite certain that if one model looks better than another, it's not because your inference algorithm is maybe a little bit better tuned to one of the models than the other, right? Or some of the simplifying assumptions you've made are more important in one model than in another. More generally, it's really dangerous to invest too much time in any particular model in biology, I would say. And part of that is what I call the Pygmalion problem, which is we tend to fall in love with the things that we work with, right? Our own creations tend to attract a large amount of our attention. And in a scientific context, we want to be driven by the desire to falsify our models, not to reinforce them. So an antidote, of course, to this is the idea that method of multiple working hypotheses. But in order to be able to entertain multiple different hypotheses, we need methods that can be applied uniformly across different hypotheses. So inference methods that are particularly useful in this are methods that have what I call the plug and play property. So this is mathematically stated as, so an algorithm has this property if it never requires us to evaluate the transition probability density. This is typically difficult for a given model, and it's the difficult part of MCMC work. So plug and play methods access this part of the model only via simulation. So it's typically quite easy to simulate in a very straightforward and unbiased way from almost any model that one would care to write down, any Markov model that one would care to write down. So plug and play methods are another synonym for them is their simulation-based methods. All right. So there are a wide range of different methods that are available for this. There are some that are based upon extracting features from the data. So approximate Bayesian computation, synthetic likelihood approaches are some methods that have been proposed and widely used, but they are all based upon reducing the data to some set of summary statistics, right? So here what we're doing is we're reducing the data to some set of summary statistics. These can be contrasted with methods that are based upon the likelihood itself. So they are maximally efficient in that sense. They are full information methods. They throw away, in principle, no information. And the two main approaches here are sequential Monte Carlo and particle Markov chain Monte Carlo, which I will describe in a moment, and iterated filtering, which is a maximization technique based on sequential Monte Carlo. So I'll skip talking about the synthetic likelihood. We can come back to that. The particle filter, this is pseudocode. I probably don't have time to go into detail on the pseudocode of this, but it's an algorithm that exploits the particular structure of the partially observed Markov process to perform that integral in an efficient way, sequentially. One can, if one uses the sequential Monte Carlo algorithm that I described here to evaluate the likelihood, it's a nice result that the likelihood estimates that one gets in that way are unbiased. They have a Monte Carlo variability, but they're unbiased. And then one can therefore sort of embed them inside of a standard Markov chain Monte Carlo Metropolis Hastings kind of algorithm that forms an accurate and perfectly adequate, quite efficient Bayesian approach to solving the inference problem. All right. Iterated filtering is something that I've been involved in the development of. My longtime collaborator, Ed Ionides, really invented this algorithm. And this is a likelihood maximization approach that works for sequential Monte Carlo calculations. The easiest way to think about it is it's a kind of an evolutionary algorithm that involves a population of parameter values that evolve to maximize the likelihood. But again, I don't want to spend too much time going through the details. I can come back to those questions by all means if there's any interest in talking about that. So assuming one can actually estimate parameters and compute likelihood so one can compare models, one is left with sort of what are the criteria that one uses? And so it's quite interesting if you read the literature on these are some of the criteria that actually appear quite frequently in the literature, right? So the best model is the one that agrees with results that already exist. And this is unfortunate from a variety of points of view. especially if one understands that as scientists, we're most interested in discovering new things. The best model is the one I can estimate before my thesis is due, as it has certain practical, compelling nature. Leaves something to be desired from the theoretical point of view. Best model is one that best agrees with my preconceptions. This is related to some of the other ones. And I'm afraid that this is quite commonly the case, that this is the model that gets published. The best model is the one that makes my supervisor the happiest. Okay. An interesting one that I see come across quite a lot, especially from students, is that a model for which I can estimate the parameters precisely is a better model than one that I cannot estimate the parameters precisely. And it's worth thinking a little bit about that, because to the extent, of course, to the extent that our goal in looking at a model is to estimate some parameters, then of course a model in which I can't do that is useless. But from the point of view of actually explaining data, the identifiability question is really secondary, right? A model for which I cannot estimate the parameters accurately might explain the data much, much better than one in which I can estimate the parameters accurately or precisely. So, it's worth thinking about that a bit more carefully than I think most people do in their standard training. And related to that is the idea that precision of parameter estimates is an indication of quality of an explanation, and of course that's simply a misconception. So when we want some examples of valid model comparison criteria are things like, how well does the model fit the data? And in answering this kind of question, there are some practices that I think are not as widespread as they ought to be. So very simple models can be quite useful, even if they're poor explanations of the data from a mechanistic point of view. To the extent they provide benchmark values of the likelihood, they provide a sort of objective benchmark comparison against which mechanistic models can be compared. So we often are in the practice of fitting even non-parametric or very generic time series models to data, because the likelihoods we get for those models give us an idea of a sort of baseline predictability that we can ask, do our mechanistic models do better than that?
Can I ask you one question? Sorry, somebody else wanted to ask a question. Well, okay, I just go ahead. I mean, you might talk about it later, but I mean, the oldest and best known model comparison criteria is not on your list, and that's Occam's razor. Why is that?
That's an excellent, it's a really excellent question. I think I will talk about that a little bit later. I certainly love to talk about that. So let's keep that in mind for the discussion afterwards.
Okay. Yeah.
If I don't come to it in the next few minutes. So it's a really excellent point. So does the model fit well at all is an important question. And then I think much more difficult to talk about, but even more important is how the model explains the data. By what means does the model, what mechanisms are evoked or invoked to explain the data, right? So that breaks down into sort of which aspects of the data are explained and which aspects are ascribed to noise. So as I mentioned before, part of the goal in using a stochastic model is to account for the data by whatever means. And then having accounted for the data, one can then ask whether one is using stochasticity to explain the data, in which case one really isn't explaining it mechanistically, and to what extent one is using the mechanisms to explain the data, and then which mechanisms one's using. So this is an important aspect of sort of where we can delve into the structure of a fitted model and see, sometimes learn quite a lot. There are questions about model adequacy as well. And I'll pass over these for now. So there are various objective things that one can do, like attempt to use a model in prediction mode, forecasting mode, and actually forecast out of sample predictions, whether forecasting forward in time or predicting the effect of various manipulations. Importantly, I think something that's not as well appreciated as it should be is that the parameter estimates themselves can be viewed as model predictions. Frequently, I find students want to take all the parameter estimates they can get from whatever source and sort of build them into the model on the theory that they'll improve the model by so doing and eliminate the uncertainty. And, so there is a logic behind that, but I'm often advocating not doing that. In fact, fitting the model to the data without using any of the preconceived parameter estimates, and using then the parameter estimates that one obtains as predictions that can be compared against those other sources of data. And I think this is useful from a number of points of view. When you make strong assumptions about parameter values, regardless of how well you base those are drawn from another source of data, often from a system which differs in some ways. And so you can actually be blinded to the fact that those assumptions are incompatible with the data that you're studying because you simply assumed the problem away. Whether you do that in a hard way by fixing parameters or you do that in a soft way by assuming priors, you can blind yourself to discrepancies between your data and the model. Whereas if you take the fitted parameters and use them as model predictions, you then have another point of comparison to criticize your model. And so that's important. There's also, I think, an aspect of fertility in terms of a good model makes testable predictions beyond maybe even what you imagined it might. And so that's an important aspect of things. So I'm sort of throwing out a bunch of stuff that I hope we can talk about later. So to come back to these specific examples very quickly, in the endemic cholera case, here's an example of an inference that we performed on the basis of those data. So we estimated the duration of the immune period using something called the profile likelihood, a very powerful technique that I think is not as widely appreciated as it should be. But when we were able to do that, we were able to derive that the duration of immunity, that the data had a very strong opinion. The duration of immunity needed to be quite short. So on the order of weeks to maybe 1 or 2 months, and that the data really didn't like even an immunity that lasted as long as 1 year. And that was really a problem, right? Because this prediction that the duration of immunity should be quite short seemed to directly contradict lots of clinical evidence that patients that are infected with cholera and survive very rarely get another case of severe cholera for many years afterwards, several years anyway. So what's going on? This is a prediction that seems to be falsified by other data. So to get a sense of what was going on, we delved into what was happening. And so in this diagram, we vary the duration of immunity along the x-axis, and on the y-axis, we look at the log likelihood. So as the log likelihood gets small, the fit to the model gets worse, right? And up here, it's you might say statistically consistent with the data. If you vary that same parameter, the immune period, across this axis, but instead of tracking the log likelihood like I'm doing here, you track the case fatality rate, so what the probability of dying given that you're infected is, you see that in this range here where the immunity is very short, the fatality rate is very, very small. By contrast, in the same period of time, physicians were reporting that the fatality rate for cholera infections was on the order of 50 to 60%. So that's way up here, right? And so we begin to see what the model is saying is that you somehow want there to be very short-lived effects of immunity, but you don't want those to, those can't be the same people that are dying, right? The people that are getting short-lived immunity can't be the same people that are dying. So the reason for that is quite clear. If you look at the data, right, you've got these incredibly explosive outbreaks of cholera that infect a very large number of people, and yet they come to a stop. And then they crash again, only to be repeated the very next year. If we had long-lived immunity and all of these people that were infected and survived were immune, we would have we'd find it impossible to have sort of repeated epidemics every year. So you can then go deeper and ask, well, is it necessary that all infected individuals be equally infectious in this model. And for example, we might imagine that there's two classes of infected individuals, some that are quite infectious and at risk of dying, and maybe others that are very mild symptoms or even asymptomatic. And when you do this, you get a case fatality rate here, which is much more in keeping with what was observed historically, and a duration of immunity amongst these severely infected individuals that's much more in keeping with what was observed historically. And so you're using the data to sort of, and the model to sort of pull yourself along and look a little more deeply at the data in a different way. Importantly, the ability to do this, to simply propose a new kind of model and effectively perform inference on it, it depends upon this plug and play property quite strongly. So one can do the same kind of thing here. I don't have time to go into the details. Unfortunately, I've talked a little bit too slowly about some of these things. There's loads to talk about here, so maybe we leave it for discussion. But there are similar kinds of conclusions that one can talk about there. So I talked a little bit about the various approaches to inference, and here's an attempt at summarizing the sort of pros and cons of those different approaches. There are is a robustness efficiency trade-off in the feature-based methods. There are trade-offs even within the full likelihood methods, which of course are computational rather than inferential. There are trade-offs associated with different inference styles, frequentist versus Bayesian inference styles, and so on. But we don't have time to talk about that. What I really think is a real possibility at the moment is a more fully integrated approach. Whereas instead of sort of picking a particular inference style and learning only that and following only that, it's possible to adopt a variety of different approaches for different portions of the inference process. The estimation, the prediction and uncertainty quantification, the diagnosis of model misspecification, and other forms of model criticism. Different algorithms lend themselves to different phases of this integrated approach. So just to sum it all up, the key in all of this is modeling the error. The plug and play approaches, because they place such minimal restrictions on the form of the models, really allow us to investigate a wide range of hypotheses. There are efficient methods that are plug and play that one can use to estimate models of wide range of forms. And there is certainly a need for more methodological development. So I'll stop there, and I hope we have some time to have a bit of discussion of any of the points that you found interesting. But thanks again for your attention.
Well, thank you very much, Aaron, and we should really thank you.
Thanks.
Yeah, maybe David, do you want to manage the discussion? Is that okay?
Yes. So whoever wants to make a question, so can
maybe I'll stop sharing my screen for the moment.
Yeah,
I can see people more clearly.
Well, I would have a question, but I saw there was a hand raised. Or should I ask a question?
Yes, of course.
So for me, a fundamental problem in model selection, and that occurs again and again, is indeed the problem of the fundamental choice, whether you have to change the mechanism of the model. So you have different model alternatives and different models with different parameters, for example. And the other option is exactly what you also did, is to introduce some noise in order to say, our model might not be perfect, but so we have some stochastic process in the background that models somehow that we have neglected certain ingredients in the model. So I didn't, of course, so quickly. I didn't understand completely how you did this in your algorithmic approach. But
Right.
is there
So
any comment in general you would like to do about this problem?
Yeah, I think so. I actually think it's not an alternative. I think that we should always. So I'm going to advocate, right? And I realize, of course, anytime somebody makes blanket statements, you take it for what it's worth. But just for the purposes of sort of stimulating discussion, I'm going to advocate that we should always be using stochastic models, regardless of whether which mechanisms we have in the models. And the reason is that you need the stochasticity to account for the things that are missing from your model because without the stochasticity, you cannot explain the data properly, right? So maybe put it the other way. So you need the stochasticity to fit the data, and the presence of stochasticity will not only to some extent, make up for lacking, so sort of missing or incorrectly specified components of the deterministic portion of the model, but it will also allow you to diagnose that very fact. So in a study that I didn't show you here, we showed how you can, by fitting the stochastic model, you can examine the properties of essentially the residuals from the stochastically fitted model and compare those against their theoretical properties to diagnose the fact that you're missing certain components of the model, and even to get a guess as to what form those should have. So my point is not only that stochasticity will improve the models, but that it improves our ability to work with the models. Of course, the price you pay is that it's much more difficult to work with stochastic models, right? Computationally and theoretically. But I think that in the sort of spirit of provocatively advocating, I will say we should always be doing this, because what we stand to gain is so much greater than the computational problem we solve. We just need more computers, whatever. We solve the computational problem, but that we stand to gain so much from doing that. And so this puts your earlier question about Occam's razor into an interesting light, right? Because in some sense, noise is a kind of very, very parsimonious way of explaining data, right? You're saying, well, there's just something else happening there, right? And the question that you have about whether the data really can support an additional term, an additional mechanism, or whether we've already gone too far and are sort of multiplying entities to explain things is a question that you can definitively answer. Right. And the way to answer it is, one way to answer it is to look at the curvature, of these likelihood profiles. Oh, is this going to work? Let's see if I can. So the curvature of likelihood profiles these are some more likelihood profiles, is a direct manifestation of the information content of the data relative to that parameter. And so in places where you see a likelihood profile that's really quite flat, it's a direct answer to the question of how much information is there in the data about that parameter. And so it's quite flat here. It's saying, well, there really is not very much information about that parameter, that any parameter value within this wide range is compatible with the data. And in some cases, it's really completely flat, right? And that's actually really important to know, because it's telling you that the data simply don't have the answer to your question. What I tell my students is that it's not a sin to ask a question that doesn't have an answer, right? It's only a sin to think that the data have an answer to that question when they don't. And so from that point of view, a method like these full information methods that allow you to know not only what the answer to your question is when you can get the answer, but also when you need better data to get the answer to your question, that's worth knowing, right? So I think this really like operationalizes Occam's razor in a sense. It really gives you a way of like putting Occam's razor into practice in a principled way, instead of just in a kind of a generic sort of, I prefer more parsimonious models kind of way.
Could I just add on a little bit? Just I don't want to disturb other questions, but because it's really fitting to that kind of problem you just described. So would you actually recommend going first to the stochastic processes from a general point of view, you know, so having little mechanisms still inside? By mechanism, I mean now causal relationships, which you would identify with deterministic thinking. And then, you know, you would try to derive a kind of a more deterministic model like a stochastic differential equation. Or would you prefer to go the other way around? So you start with a deterministic model where you have full control of the mechanisms, and then you just you make it stochastic afterwards, either through the parameters or by introducing this white noise in the stochastic differential equation.
That's an excellent question. I think it's very, very interesting, and I don't you know, if you'd asked me that question 5 years ago, I would say I had a strong opinion that, you know, that the model should reflect the question that you're trying to ask. And so to the extent that we think in terms of deterministic mechanisms, that, you know, the second approach that you describe of taking some deterministic model and elaborating it into a stochastic model by one means or another is a sensible way of getting an answer to your question. I think, you know, just as a parenthetical remark or an asterisk, I would say, you know, that many students often set out, they say, well, let's start simple. Let's take a deterministic model, fit it to the data, and then we'll add stochasticity. The problem with that is that you don't necessarily learn very much from fitting the deterministic model to the data, because the mode of the various modes that are available to the deterministic model to fit the data are in many cases quite distinct from the stochastic model. And so, you know, if you got like sort of approximate parameter estimates that you refined then by adding stochasticity, that would be justifiable, right? But to the extent that you may get estimates that are very widely separated, it's sort of sometimes a fruitless exercise. But your question was actually deeper than that, right? Your question, you actually proposed the idea of starting with something which is quite non-parametric, perhaps, and then trying to deduce the sort of deterministic things that are there. And I actually think that's an extremely interesting idea. And my understanding is that you guys have been thinking a little bit about this, and I'm quite interested in that. We've done a little bit of work sort of along those lines, where we're looking at infections and how they unfold inside of a host. So it's a malaria system in a mouse, which is nice because you can take time series data of parasite concentrations and blood cell concentrations every day for the entire course of the infection and see how the thing unfolds. But the problem is the immune system is this horribly complex thing, right? And, you know, if you were to sit down there, if you were to say, okay, I'm just a poor mathematician, let me go to an immunologist and ask him how to write down the equations, you know, forget about it. I mean, you know, it's essentially impossible, right? I mean, partly because the immunologists are discovering new things every day, right? So the thing is constantly changing, and so the list of equations just gets longer, and partly because, of course, that somehow misses the point, right? Because the immune system, by its nature, is highly reticulate, highly redundant, and its modes of operation are, of course, you know, emergent out of all of that complexity. So we're very interested in trying to come at it from a sort of a non-parametric approach in order to work out what the effective degrees of freedom are, and then see if we can't deduce something. So I'm very interested in this. If you guys have any ideas about that, I'd love to hear what you've been doing.
Yeah, well, we should continue the discussion some other time. That would be quite nice.
So let me just I see there is a question by Lennox Koopman that he may want to rephrase himself.
Yeah, sure, go ahead.
Me reading it.
I didn't want to interrupt you during the talk, and it might be a very specific question, but when you had a slide about finding the solution to the Markov models you had, and usually I hear more often about the Viterbi algorithm than I hear about Markov models, and I'm not sure. You didn't mention the Viterbi algorithm, did you?
Well, no, I didn't. But
Okay.
let me explain what that is. So, I mean, you probably know what the Viterbi algorithm is, but
Kind of. That is another thing. I never used it.
right.
I hear it more often from electrical engineers who don't even know what Markov processes are. And it was on my to-do list. That is what
Sure.
I can say.
So it's very interesting. The literature on this subject is quite fractured, right? So there's multiple groups of people working in ways that don't using the same models, but they don't understand that they're the same models because they use different language. So there's a class of models called hidden Markov models, which essentially is identical. You can certainly make the mathematical definition such that it's identical to what I'm calling a partially observed Markov process. But in the sort of milieu of the people who work with hidden Markov models, those are typically finite state. So there's a finite number of states in those systems. So they're interested in language processing. And so they've got a list of words that, they're interested in descriptions of how those words, or they're interested in behavioral elements of animals. And so they shift from feeding behavior to mating behavior to whatever, and so on. So there's a finite state. And then for such models, if your model is essentially, if you've got a finite state Markov process, right, the model is basically a matrix of numbers, right, probabilities. And so, if you want to estimate that matrix, that's what the Viterbi algorithm is for, right? So the Viterbi algorithm is essentially an algorithm that computes the likelihood in that way. It uses, so mathematically, it sort of uses exactly the same equations. It's just that all of those integrals become finite sums, essentially matrix products. And so you can, in the finite state case, you don't need to use any fancy sequential Monte Carlo, because you can sort of explicitly calculate everything, right? Numerically, it's just a finite calculation. What happens is in the situation where the state space becomes infinite, or really just when the number of states becomes large, right? So suppose we've got an SIR model in a population of 10,000 people, right? Then, the state space is sort of 10,000 by 10,000 by 10,000, right? So what is that? 10 to the 12th, right? And so it's a bit inconvenient to be multiplying 10, matrices with 10 to the 24 entries. So, anyway, so that's why the sequential Monte Carlo algorithms are used.
Thank you. That helped a lot, because I was thinking about how to increase the number of states with the Viterbi algorithm, and I feared that there's something I'm missing. So that was just the point I was searching for. Thank you.
Yeah, and so it turns out, the people who work on the hidden Markov models and the people who work on, another name for it is state space models, they tend to not talk to one another very often for whatever reason, even though they map onto each other very nicely. Great question.
Yeah, so is there any other question? Otherwise, I would I think now stop the recording.
Yeah, well, let's ask a little bit another question, just to. So probably was implicit in the algorithm, or in your words, that in order to have flexibility, model specification, and so on, you simulate your system. When you simulate your system, are you using Gillespie algorithm?
Well, there are a variety of different algorithms one can use to simulate, and so the usual considerations of computational efficiency versus accuracy come into play, right? Just as if we're solving, fluid dynamics equations or mechanics equations, right? You have a variety of integrators for differential equations you can choose, and they have their pros and their cons. There is an interesting dimension to this, though, which is, it's quite an interesting dimension, because I don't think people think about it very often, or maybe I have a strange perspective on it. But my perspective is, it makes a lot of sense. We mathematical biologists, if we trace our intellectual roots, we come from physics. And in physics, we have equations that are really very good, right? I mean, we can, it's not too much to expect that if you have a careful experimental design and a good theory, that you have theoretical predictions that you expect to be matched to 6 decimal places or more, right? This is not unheard of, right? In biology, hey, an order of magnitude, that's pretty good, right? So there's a sort of a revision of our thinking that needs to happen in the face of that, which I think is part of the way in which biology really does enrich the theory, the mathematical theory that we use to think about it beyond mathematical physics. And that's to do with the sort of magnitude of noise. So to come back to your question, so, coming from our background in mathematical physics, we're used to thinking, well, what is the most accurate algorithm I can have to solve these equations? Because I need the equations to match the theoretical solution I need the approximation, the numerical approximation to match the theoretical solution very well, because I could, I'm going to compare it against data, right? And if I've got, 10% error in my numerical simulations, then it's going to look like my theory is bad, but it's not my theory that's bad. It's my numerical calculation that's bad, right? In biology, it's a bit strange to have a model that you don't expect to fit the data to within an order of magnitude and be worried about whether the model, the numerical algorithm is first order or second order or third order or whatever in terms of its convergence properties. Another way to think about it is that if I write down a model theoretically on paper, and then I convert that into a simulator, and then I fit that simulation to the data using a method that only ever looks at the simulator, then what's the model? Is the model the thing on the paper, or is the model the thing in the computer that I'm actually fitting to the data? In which case, so from the statistical point of view, it's the computer simulation that's the model, right? That's the thing that's actually being estimated. And then, of course, there's still the question of how do I describe that? How do I describe that in paper and equations, right? Which is an important problem. But it's sort of the emphasis shifts subtly between those two. And I think so I'm actually a big fan of using methods that are quick to simulate, even if they're not terribly accurate, as long as they are valid models, right? Because then at least I know what I've got, and I could then ask, what are the properties of this model? For example, if I've got a step size that is variable, I can fit it with the large step size, and then I can ask, well, does the description change if I decrease the step size, right? Because then I'm revealing things that are potentially important to do, that discrepancies between the theoretical model and the simulation model. Does that make sense?
Yeah.
Yes.
Long answer to a very simple question, but I think it's an important one, right? I think it's very strange, right? To be very concrete, it's very strange that a lot of people are concerned about, they like the Gillespie method because it's exact, but it's an exact solution to a set of equations that are very far from correct, right? So what's the point of spending an enormous amount of computing time getting an exact solution to a model that you're going to reject anyway?
No,
right?
no, I wouldn't agree with the last statement.
Yeah. Okay, maybe that's too far. Well, of course we're going to reject the model, but my point is that typically the errors we're concerned about are not in the numerical approximation. Those are small relative to the other errors.
But I mean, I will make a comment with respect to this, because in the case of the Gillespie algorithm, there is not only a problem of, not a problem. The algorithm not only solves correctly the equations, but actually is respecting somehow, let me say, the physics of what's happening. So in this context, I would say that for sure, physics in some sense is much simpler than the biological system. But on the other hand, somehow contains, the logic of the algorithm contains the idea of considering the interaction of single or in susceptible and infected, or
but it's really important, Luca, to it respects those aspects of the physics, but those are not by any means the most important, right? So think about this, right? So there's so many ways to think about this. Certain aspects of the physics that the Gillespie algorithm respects are very important, right? You don't have creation of people out of nothing, right? You don't have people just disappearing. You have conservation of individuals on some level. You have transformations of state that occur in particular ways, right? But of course, it's possible to enforce those constraints in a variety of ways, right? So it's not unique to the Gillespie algorithm. The Gillespie algorithm really relies upon demographic stochasticity being the only form of stochasticity. The sort of intrinsic noise is the only kind of noise.
Yes,
but in any real system, there's extrinsic noise as well. And that extrinsic noise is both extrinsic in the sense that the environment fluctuates, but it's also extrinsic in the sense that things don't conform to it's a noise that enters because things don't conform to the simple assumptions of the Gillespie algorithm. So you might think what could be more reasonable? A susceptible individual and an infected individual come together. That results in two infected individuals, right? But what happens when an infected person steps onto a crowded bus?
Yeah, that's true.
So you can say, well, over the time scale of infection, okay, it's one infection leads to another infection, leads to another infection. But over any reasonable time scale, that's an event that results in 50 infections, right? It's a totally different kind of thing. And so how does that show up? Well, it shows up as extra demographic stochasticity. And once you've got that, the Gillespie algorithm is not exact anyway, right? So in some sense, I feel like
it's a problem of scaling. It's essentially a problem of scale. Okay.
Yeah.
It's a time and space scaling and size scaling because
and so there's a sort of as a field, we're sort of enamored of the lovely, very elegant theory associated with those kinds of processes, because it maps from the microscopic to the mesoscopic to the macroscopic in a beautiful way. And David has done a lot of really nice work on exactly how this is done, of course, and that's lovely. But the nature of the uncertainties in real biological systems is not so neat.
Yeah. Of course, how you call it? We have this. Sometimes we have this problem of falling in love with what we really know how it works.
Yeah.
But I like your perspective. Yes, thank you.
Thank you. Yeah, really great questions. Really fun talking to you guys. I see a lot of it's great because there's a small enough group of us that I can actually see you, or I see most of you anyway, and I can see the light in your eyes, which is great. Much better than most other experiences we have these days. Anyway.
Yeah, no, it was really a very nice talk. Is there any other question?
Maybe a completely different question. If you could make a wish for the perfect data to parameterize your model, what would that be?
For what kind of a model are we talking about? Like some of these that I was just describing?
Yes, this you are describing.
Yeah, that's a really interesting question, actually. It's interesting. So there's so many things to say. So one thing to say is that a really nice feature of the partially observed Markov process structure for class of models is that in principle, many different kinds of data from very different kinds can be integrated into it, right? You have to probabilistically describe the relationship between the state variables and the data, but as long as you can do that, then you can incorporate all kinds of data. So in some sense, the answer to your question is doesn't matter. The more, the better. But that's of course not really true. So obviously, you know as well as anybody the importance of the timescales and and so on and so forth. So an interesting thing I can say is that sometimes too much data is a problem, right? And the reason for this is that it's related to the relationship between the information in the data and the curvature of the space. So the more information we have, the more tightly curved the space, the more sharply peaked is the likelihood the maximum of the likelihood, the region that we're interested in. And so the harder it can be to find that when there's a lot of data. And in the limit where the data are deterministic, for example, they're assumed to be infinitely informative, right? The precision is perfect. Then these things can become pathological. And you can have, for example, if you've got chaotic dynamics and you make the assumption that the observations are very good, then you end up with sort of fractal structures potentially in the parameter space, and the whole thing is very different. Interestingly, once you add stochasticity, a lot of those things go away, which kind of comes back to the question we were having before about the relationship between deterministic and stochastic dynamics. Many of the sort of pathologies that arise in deterministic systems are just simply not present in the stochastic system. So which makes you wonder what the meaning of those pathologies really is. But there are some real challenges too to getting new data sets, right? So one of the forms of data that are becoming much more prevalent in the context of disease transmission are genomic data, right? So we have millions of pathogen samples being collected from COVID patients all over the place. Those are sequenced, and they can often reveal, I mean, it's difficult, but they can often reveal quite intricate family relationships amongst different pathogen lineages, right? So we know, something about when they divided, these family trees divided from one another. And but it's a challenging problem to sort of integrate those data with the kinds of models that I'm talking about, because fundamentally a genealogy or a phylogeny, a family tree, is sort of something that is backward looking in time, whereas these stochastic processes are famously difficult or impossible to actually study backward in time, right? They're highly dissipative, they're non-reversible, so going backward in time is not really an option. And so some work that we've been doing very recently that I'm quite excited about is sort of doing the math to figure out how to bring those two things together. Stochastic models that you can only simulate with genealogical or genomic data. And so that's a very interesting class of problems.
Is the answer not simple? I mean, you would, of course, need to embed it in some kind of evolutionary structure.
Well, that's not even necessary, right? A lot of times what you're looking at very small mutational differences amongst the strains, and you not even need, of course, if there are strong evolutionary implications, that makes it more difficult. But often one is looking at these mutational differences as merely markers for how distantly separated two strains are from one another, right? So one is really only, one doesn't even need an evolutionary model, right? You simply just need a model that you need to understand the connection between the genealogical data and the Markov process on some level.
Yeah, I mean, for example, for your cholera example, it is very likely that if, for example, if the cholera does mutate a lot, that that the waning of immunity is not just because of your immune system, but it's also just because you have a different virus or a different bacteria, whatever it is. And that changes the perspective. So what I mean by evolutionary model is, do you still have the same kind of infectious agent as before? And if not,
right,
of course, you would have to adapt your model.
It's true. It's true. Absolutely.
Well, I really would like to invite you, to have more discussions. It would be nice if you can give us your expertise a little bit in future whenever you have.
And vice versa. I'd really be interested in hearing what you guys, like I say, have been working on lately. It's David just gave me he sent me a preprint, but I'll maybe I can contact you again soon. Yeah, it'd be best. I'd love to, perhaps if I'm in Europe at some point, maybe I can swing through and visit. I don't know if are you still shut down quite strongly?
no, everybody is now opening up, every country, so it should
Yeah, it seems to be.
increasingly become easier and easier, I think.
Yeah, it seems to be the case across the board. So that,
Yeah.
perhaps at some point soon we could do
Maybe
that.
not in Hong Kong, but that's an exception, I think.
Yeah, well, thanks a lot for the invitation. It was really a stimulating discussion. I really appreciated the chance to chat with you guys about this stuff.
Yeah, then I would like to thank you again,
Thank
and yeah, hope to keep in touch. Yeah.
Okay, thank you.
Thank you.
Bye-bye.
Have a nice evening.
You too.
Yeah, you too.
Bye-bye.
Bye-bye.
Have a nice evening, King. Aaron
Cheers.
King.
All right. See you guys later.
See you guys.